Hey, how's it going, everybody? It's Liv, and you read the title of the video. We're going to be doing quote unquote the allocation, deallocation, and reallocation, all three of them. But we're not gonna be doing it in C per se. We're going to be doing it Perl. So interesting. So all right, let's get this let's get this out there right now. All right. We are utilizing, well, actually this one, we're utilizing this block class that I wrote some time ago, and now I've been rethinking it. Um, Basically, what we are doing, if I go into the constructor, we have a mem value, which is simply a buffer. All right, think of it as a string. All right, it's a byte array. Okay, so not a string of characters. That's like its own concept. And it would include like like UTF-8 stuff and spooky shit. Now this is just a bytes array, okay? All right. So hold that thought. We also have this thing called grow, and what grow will do is it will concatenate to that string, okay? So we have a string, and we grow it by some amount, and that is our bytes array, and then we just mess around with those bytes. So let's see what that looks like. We are assigning this symbolic constant to each and every slot that we allocate, and the size of the slots, I'll get into that in a second. But for now, just think of that. Okay, so we grow or mem by some amount, and we set it to this constant free block. Okay. So let's see how that looks, and let me just comment out the irrelevant stuff. And let's just grow by a factor of 16, okay? So that would be 16 bytes. Okay, let's run that, and I'm actually going to zoom in here a little. Okay, so let's just run that test, and oops, I'm sorry, I forgot the breach. Okay, there we go. And as you can see, we have what? Two 8-byte blocks with the peso money free block constant assigned to them, right? So this is the 8-byte value of free block. All right. So I promised I would talk about sizes of each block. So the way this works is we have something called a unit, and unit is something like what you generally know as word size, which I think is a little bit misleading, but the term is generally known as word size. Okay, so word size, and that generally means the capacity of your general purpose register, right? So we have AIX for 32-bit and RIX for 64-bit, and this would be a 32-bit register and a 64-bit register. So here you can have a long, and here you can have a long, right? But yeah, and just to add to the confusion, this is what I consider a word, and this is what I consider a long. So yeah, just adding to that misnaming and misleading naming conventions. But anyhow, because we target exclusively 64-bit, the half value, which would be the word size, and actually unit would be 2 halves. Okay, so a half is the register size, unit is 2 halves. Okay, so why? Historical reasons concerning the system, which I don't want to get into. But anyhow, we are targeting 64-bit, so we know that half is always 8 bytes and unit is always 16. What does this mean in practice? As you can see, unit is the alignment. Thus, every time we grow the block, we want to grow to a quantity that's aligned by this amount. What does this mean? If I try to grow by 15 rather than 16, it will still give me 1 unit, 1 whole unit. If I try to grow by 17 rather than 16, it will give me 2 whole units, right? It will not give me, like 1 unit and 1 byte. No, it will give me the whole thing, right? So why is that? Well, because first and foremost, we want every allocation to have an address that it's a multiple of 16. Okay, so that's why we call it an alignment. Okay, so the address aligns to 16. And why is that? Because it is mathematically convenient. If we want to know if an address is the start of a block, all we have to do is say take address and end it with the first 4 bits. Okay, so if this holds true, then it is not. Okay, so is a block, we could say, no, let's say address is block. Okay, we could say it like this, right? So it equals to address does not have those first 4 bits set. Okay, because in hexadecimal this is 16, and so every multiple of 16 has this lower half set to 0, and this thing set to any old number, right? So from 1 to f. So arithmetically it's convenient. What is the other benefit? Well, we can get into that, but in order to get into that, let's try doing some allocations. All right, so we already have a little mechanism to sort of ask for a memory equal to the size of some type. And as you are able to see, we have a mechanism for declaring structs, right? So here we're just doing 8 bytes and a long, and again, long is 8 bytes, right? So basically 8 bytes and 8 bytes, all right? We do have to take that type. Oh no, I can just say my type equals initial constructor. Yeah. Okay, so all right, and we can make an allocation, right? So we have an alloc method. What does this do? We takes a name of the block we want to baptize, as we say, the type from which we derive the size, and then the count, right? So basically this is just a straight up multiplier. What grow gives us is the new how to say, the number of bytes allocated, and besides that the offset, and so the position, right? So the position within this stack, you could say, this stack of units, the position onto which our new block begins. All right, so we have enough information there in order to baptize the block. And baptism, all it does is it creates a pointer. And the way pointer works, it's not like a one-to-one correlation between C pointers and this class over here, but it's a close enough thing that it merits having the same name. It's the closest thing I could get to it. But anyhow, basically what we do is we take all of this type and block information, and we utilize that to point to a particular slot, to a particular section of our mem, right? So what we have in here, this is the mem string, right? So this is the string broken up into bytes, all right? And we can utilize this very useful back function in order to take like a slice of that string and then modify that just independently. And this is really cool. You can actually take a reference to that. And so then you just say pointer, and you can just say and equals, or XOR equals, or and equals, or just equals, or times equals, right? So whatever operation you would want to do, you can do. Okay. So here's a little bit of a thing, and I'm going to get into it because things come into my mind as I demonstrate this. So here's a little bit of a thing. First, I'm going to show you what the allocation does, and then we're going to delve into the gritty details. Okay. So all right, let's just allocate this and preach it out. Okay. So all right, we get just a single line because we have this thing that is it's exactly 16 bits. What if we have 9 cars, 9 bytes instead of 8? Well, let's take a look. We get an additional line. Why is that? Let's try doing some fillings in here. Okay. As you can see, the first 9 bytes are for our bytes, but then it goes on to the next unit, right? It doesn't fill out this this long value. It doesn't put like the first 7 bytes in here and then the last one in here. It doesn't do that, right? Well, this is just because yeah, this is like the better way to do it. If you were to pack this as you would get with the Pragma pack, and if you don't know what that is, why did you click on this video? If you were to pack this as with the Pragma pack, what you would find is then in order to retrieve and in order to read and write to that value, you have to do like 5 more operations. It's stupid. It's something that doesn't work and should not be supported, and so we do not support it. I guess there are use cases for it. For instance, when you are compressing data, in that instance, yeah. But I mean, if you are compressing data, then you would have to think of it differently. I would make every member a byte to begin with, or a short, but I would make every block equal sized and then just assign the bits as necessary. But in any case, when you are compressing and you intend to read that back, yeah, you don't intend that to be instantaneous. However, when you have data in memory, you do intend for it to be as fast as possible, at least if you know the first thing that you should know. Anyhow, so there is one thing, right, about this thing. And if we say we want 4 bytes, what happens? Well, this mess. Wait, I have to change this up. Okay. So again, we don't try to fit the first half in here and the second half in here. No, we need 8 bytes. We need 8 whole bytes. We will not we will not try to fit half and half, right? So yeah, that this is the way it is supposed to work. And if you look at the way that that most C compilers will handle your structs, you will see that they do exactly this. That's just learn memory alignment. You must, right? It's your destiny. Likewise, if we give 5 bytes instead of 4, we do get our 5 bytes on the first half, but the second half entirely for the long. Okay, well, that's about that for that piece of the demonstration. Let's move on to something more interesting. So, just a little comment on the nature of grow. As some of you might know already, this is not a one-to-one again, it's not a one-to-one correlation to the way that actual memory allocation would work, right? So this is, more of a I can do it this way because it's an interpreted language, I'm just gonna, right? But anyhow, what you would know is that, what you may know is that this is very similar to, I think it's a syscall, which is sbreak or break, one of the two or both, which basically does that. It just moves the breakpoint of a program, so it enlarges the data segment, right? So this is similar to that. The difference is that sbreak would give you increases in it would use the page size for that, right? So you have like a memory granularity, right? So that's the granularity that sbreak would handle. And if you're in a more modern API, you would probably be using mmap, right? Like if you have mmap, you should be using that. But anyhow, mmap as well will give you memory. Not you can't just ask for 8 bytes. It will give you like a whole bunch, right? So generally it would be 4K, right? So 4 kilobytes. Sometimes in some architectures I think it's 16. In some others I think it's 64, which blows my mind. Like, whoa, that gargantuan quantities of memory. But anyhow. Grow is not really giving you that much memory. It's just giving you increases of 16 at most, at least. Well, why is that? Well, because yeah, just for demonstration, if I were to get like a whole page, like you couldn't see it in the screen. Like it would be a pain to demonstrate this functionality with that kind of size. And besides, just because I can get away with it, it's easy to do it this way. Because else we would have to, get the entire page and then just assign like little indices onto it. We will have to make like a full-blown allocator. We're going to do a halfway allocator, all right? Just using these functions, and another one that I have to think up. So, how do we deallocate? What is freeing memory? What is it even? Well, if you recall our little demonstration with grow by 64, you see that it gives us this thing with a free block, right? Now, if we, instead of doing an alloc, which is a grow and baptize, so baptize is basically just how to say, is segmenting a particular section of the block, with different elements, as in a struct, or you could also do it with primitives. Okay. So let's say none want to baptize. Let's give it a name, just a primitive, and we are going to be using I guess word, why not? And I don't remember the rest of the arguments, so it's name type offset, right? So let's say offset number 0, and let's get 2 whole 4-byte words. Okay, let's try that, and oops. All right, give me a sec. I need to... Oh, right, I get it. Because it's a primitive and it's trying to get the size from this thing. Just a second, I have to debug this real quick. So let's just use fmat and fat dump to get the entire friggin' structure, and we can debug from there. So fat dump the type, and let's see what that looks like. Okay. So it does have size, so why is it registering it as undefined? I suppose it refers to this one. I suppose that because I asked for 2, right? So I actually have 2. Is it instance count? Yes. You actually have to multiply this. Okay. And now it should be just fine. There we go. Okay, fixed. So all right. You can see that merely baptizing a section, it would just float fill it with zeros, right? And again, it will float fill the entire unit, right? We only need the first half, but it is going to baptize the entire section. Now, this entire section belongs to this pointer, so to speak. You know, we could baptize with a different subdivision. So, for instance, we could say, let's do this. Let's say world and wide. Let's claim 4 of these, okay? And this would still work towards the same section of memory. Right, let me just clear that so it's on top. So I can take this and say, let's say A and B. Why not? And to A, let's set B. It's 2 values, so let's say DDD and FFF, something like that. Right, and it fills it up, right? So we have these 4 things, and now let's actually be a little bit more tricky this time. Let's take from the buff. So this is like the set of elements we have. Let's take 1 and 2. Let's say R, console this, and let's just map this thing. So I need to reference this. Oh, actually I can say arg. There. there it is. Okay, and I can assign to this something like 111. These are shorts, so yeah. Let's actually do it. I don't know what. This is gonna be fine. Okay, and let's try that. Oops. Okay, there we go. Oh, not quite. Not quite. My indexing was off. Okay, so okay, you are messing with my mind. All right, there we go. Okay, so here is, so all of this is the first word. All of this is the second word. This is the first short, the first wide, and this is the third wide, right? So we can do unions, right, quite easily. if I set this to the first one, you see that it overrides the first integer. If I take this out and assign I don't know, I just do it like that. Now we fill this half with the word, and the upper half, right, so to speak. We filled it, or the lower half I should say, we filled it the other way around. So we can do interesting things here, and we can in fact access this part. It's just not quite as straightforward. So what's the problem? The way we asked for memory, we only asked for the first half, right? Effectively, that's what we did. We only asked for the first half, and so it doesn't bother giving us a handle onto that memory. However, we can still access it through the use of flood. Okay, so we can say a flood, flood, and let's put just null in there. Okay, and null is also another symbolic constant. It's just some value, some hexpic value, and you can see it gives us a value of dead beef, right? Let's see if that's in frame. I guess it should be. So it just gives us a bunch of like it's just like a unique value that just tells us that this thing has been fred. Do not touch it. Likewise, having free block tells us this thing is untapped, right? So it's ready for use. So what I would like to do is have a mechanism for freeing up this thing. Okay, so there's a couple ways we have to go about it. The first one, we have to actually delete these, okay, these pointers that we create, because if we go into baptize, you can see that we are stored. What you actually cannot see it. I will have to show you here the initialization. This thing we call a frame is an instance container. Okay, so basically it contains context information for every instance of a class, and this elem's value here, attribute, this thing is essentially a frame pointer, a frame of pointers. There we go, a frame of pointers. And what we do basically is we say to frame at name of value, we assign this. So right, we could totally assign two things the same value and they would overwrite each other. So yeah, we are not checking for redeclaration just because it could be something to add on to some other part of code, but for now it's irrelevant. But anyhow, so one thing we will have to do in our dealloc, and alloc, all it's doing is just grow and baptize, right? So it's just these two calls that we made just in one go. And instead of having to calculate the offset manually, it takes the offset from the grow itself, because once again, grow is giving us this offset in the form of the top of the stack. All right. So it gives us the top of the stack before being increased, and so now we have we know where to put the new block, right? So we know where we grew from, all right? So now one thing we have to do is we have to dealloc. But here's the thing, if we just free some memory, wouldn't it be nice to maybe reuse it? Yeah, but here's the problem, because we are utilizing this model that's like I told you, like S-break, right? So just growing it like a stack. The problem is this could lead to how do you say, fragmented memory? I think it is the term. Like basically you have like little empty chunks in the middle. So how can we mitigate that? Well, we would only free that which we alloc, right? What if every time we alloc, we just register the size and offset? Okay, so listen, we register the size and offset into a hash, and we check that before we grow, that there is and that there is a size available for how do you say, that there is an offset available of a certain size. So here's what we have to do. Basically, we have to take the size calculation and just shove it somewhere else. And that's actually quite easy to do. So it's just these 2 bits, all right? So we can just move this somewhere else. So let's just say sub align size, right? So size of type aligned to our alignment rules, basically. Let's just take all of this, and what we would want to return is alignment, and well, not actually alignment, just a multiplier, I guess. And we know that the multiplier would always be a multiplier of halves, right? That's sort of the idea. You can then redefine what a half is, how big a half is, and this would still work. Though honestly, I wouldn't try. Honestly, I wouldn't try. But if you want to make this exact same system, except 16-bit instead of 64, I guess you can. I guess you can, at least in some instances. But yeah, not quite. Because yeah, there are certain instances in here where it's just easier to calculate it this way, and so I do just that. Oh no, actually no, because this 8 is not for size of long. This 8 is for size of a byte, right? Because this gives us the count in number of bytes, not bits. And yeah, this hash in here is it is counting it's counting bits, not bytes, right? So 8 for single, 16, 32, and 64. If you are in a platform in which a byte is any number other than 8, well, bad luck, tough luck. I'm not going to support you ever. Don't even ask, right? Like, 8-bit bytes is just a standard. It's what your platform should use. Unless you have a very good reason not to, right? Like, perhaps someone who is more of a hardware guy could give you like really good reasons why it would be nice. It's not something I would know about. Yeah, but it's not something I've heard much of, so I just disregard it entirely. But anyhow, we need to know what the size of a block, what the aligned size of a block would be according to, wait up, oh, here we go, okay. All right. So we can actually take this in here. So I would just return the multiplier and the size, right? So the multiplier is just so that I know the amount of halves that it goes in here. And so basically you can compute the entire size of the block by size and multiplier. Now, this is for some reason this is not entirely correct. Let me see. Well, it's curious. It's not taking the size of the type itself into account. I thought that was being done. This is not right. Right, let's just fix that real quick. So line size, it should take the type that it's trying to align to, to the unit size. So we do have to take the size of this type. Okay. So it's basically not the count itself, unless I've been multiplying that, but no, I did not. Oh no. Oh. Well, that's dirty. That's dirty. Okay. So we were doing this. Alright. Okay, so let's just right. So it's just taking like a straight up size thing. But that wouldn't really be a counter now, would it? Not really. I guess you could say it is sort of like the byte count, but not really. So yeah. Let's say requested. Let's just say size, why not? And this would actually be the... Actually, this would just be constant, now that I think about it. It would always be this value. So yeah, there's no variation in this. So not much of a point in returning that. So yeah. Let's just get that in both. Yeah, I get that it is a little bit it is a little bit weird to have all of this to repeat this kind of thing, but yeah. Just to save me having to type the entire path every single time. Let's see. Right. But actually, this should be I should call it pack. Or no, I think it's format. Yeah. That's how the documentation refers to it, so let's call it that. So fmat is for format, yes. So all right. So here's the idea. We take this function, and yes, I have to finish it up, but let me have a little break. We take this function. It gives us the aligned size of a given type. Of a given type times a count. So actually, I should add that. Right. Fuck. Okay, so it gives us the aligned size of a given type multiplied so many times, align that to a unit. We take that and then we say, suppose that we have a hash. We have a hash, and we take that particular aligned size, and we say this is equal to offset, right? Or actually, we can make it a list. Yeah, why not? Let's make it a list. And so, before we try and grow, right? So before we try and grow the, how to say, before we try and grow the segment, right? Before we try and grow the bytes array, we check that we have any blocks already free that are of that size, right? So that's basis of what we have to do. All right. Now, where should we do this? I suppose that during the freeing, right? Because if we can calculate the aligned size just by the offset, if we can calculate the aligned size just by having the type, pointer already knows the type, and it knows the instance count that it was requested, and thus it can recalculate the aligned size, giving us the list of offsets. And so what we would have to do in here actually is not retrieve from here. Well, not entirely. What we have to do is a check that we have such a size within our hash, and that there are any offsets available, right? So generally, if this thing exists, then it would mean there are things available. So I would actually just do the first check. If so, we just pop the offset from here, right? So this is equal to a list of offsets, so we just pop. So we would pop from here, right? And that would be the offset, right? So actually, let's just give it a little bit like that. Else, and yeah, and size would be self-aligned size of type and count, right? So we can regenerate this. Actually, align size, yeah. Yeah, I think align is good, it's better. Just shorter. Right? So we can get this and then just retrieve from grow. Okay. By the way, what should this actually take? It should take a multiplier, right? Yeah. The alignment is just constant. We can just take that. Right. Take that, and we would have to return the multiplier. This should be, give me a second, I'm trying to gather my thoughts in here. Okay. So in here, we have to do the multiplication itself. So, my total. First we do that. Why not? Let's say requested. Yeah, why not? Or yeah, names are always difficult. Well, let's just think about a good name while I have a drink. All right. Okay. Why do it with a while? I couldn't think of a quicker way, so I'm pretty sure you can. I'm pretty sure you could do this with a division. I do not know if division is slower or faster than. Well, I mean, it is. It would be one instruction versus like a whole bunch. So yeah, it might actually be faster. Because here we have to do a comparison. First the multiplication, then a comparison, and then just adding. And yeah, we do have to repeat this process every single time. So yeah, it's actually slower. I believe this would actually be slower than a straight up division. So it would be, how many times does, well, let's just call this size. Why not? Let's say total. Yeah, yeah, total size. Yeah, whatever. Let's try this. Okay, I'm just going to ask Python. Why not? Because it's easier. Oh, wait a second. If I just say Perl, do I get like a command line? Can I say print hi? No, I cannot. So yeah. Oh wait. Because now I'm curious. Okay, let's say use v5360 and say hi. Yeah, no, that's not going. I don't know if I don't know. There's probably a way to have like a shell, like a Perl shell, but yeah, I don't know. So I'm just going to call Python. Anyhow, let's see. I want to say total over alignment, maybe. Well, let's see. If I have a 15 over 16, right? So this would be the alignment, and this would be the amount of bytes requested. Theoretically, it will give me this kind of thing. So I have to int, but the problem is it will go back. It will round towards 0. So actually, I have to just wrap this up and just add it 0.9, and there we go. Like, yeah, I guess that's good enough for most purposes. And it's just one operation, so that's kind of neat. Right, and if we do 17, it should give us 2, and now it doesn't. But I'm pretty sure that Perl would give us the right value. Let's try. Why not? So let's see. Let's say Perl E, and this time, yeah, I gotta do it like this. It's kind of annoying. To print, I want int of this plus 0.9. And let's say 17 over 16. It still gives me 1. That's not nice. Well, we know that 1 is the minimum, right? So it should always be right. Right. So I guess, yeah, there we go. Okay, all right. So it's just maths things, right? Okay. I could swear that was I could swear it would have given me the right result, but whatever. So yeah, just let me make a little adjustment here, because I was using the exact same thing, thinking like it would just clamp to what I wanted to. But yeah, never assume anything with floats. They're just bullshit. They're just full of shit. Anyhow, yeah, floats are full of shit. You can quote me on that. Yeah, floats are full of shit. Vibranca 2022. Anyhow. So yeah, we can replace this with that, I guess. Save us the trouble. Right up. Like just round up, goddammit. Like yeah. I mean, in my head, I'm trying to find instances where this would just utterly fail. Um, and I guess that there will be corner cases. So in the future, we do have to think of a better way to handle the rounding. But now, because we are just handling, like low numbers, from 16 to 128 at most, it's fine. But yeah, we do have to find a better way to round things, if possible, in the fastest way that I can think of, because it's just nice to do. But anyhow. I would return mult and mult times alignment, right? Just so I don't have to fetch this, just so I don't have to fetch this variable again, just because of that. I'm gonna have to take that on this side. Okay, let's actually say mult and offset. Oh no, wait. What am I thinking? Mult and align size. Let's equal that to this whole thing. All right, and that's a wrap, basically. So now, yeah, now that I look at it, if we are always going to be getting the size, so basically this, from another function, it doesn't make any sense to return that. So yeah, it should return like the previous stop. So actually, let's say previous stop. Maybe I could say block start. Yeah, I think that's a little bit clearer. Maybe section. Yeah, section start. Maybe segment. Like so many names I could give this. Now I'm just gonna put previous stop. Right? So it's the previous stop of the stack, right? And that's that. Like the new top for the kind of operation that we would be calling this function to do, it's meaningless. It doesn't tell us much. except I don't know, like computing the size of the, computing the size of the block from like the beginning offset and the top of the stack. But yeah, like we wouldn't be doing that. We already have the size, so yeah, it's useless. It's just useless data. So yeah, let's just take offset from this. Okay, and in order to grow, let me see, I have to pass it the mold. So right, and there we go. Okay, so now that's a whole lot better. That's a whole lot better. So what we have to do is when we deallocate, we have to, well, first and foremost, we need to create this hash somewhere. I just include it somewhere in the class. It doesn't matter, but we have to define this hash, and in the allocation function, or I'm gonna call it free just because it's not actually shrinking, right? It's not actually shrinking the mem. It's just freeing it, right? So just letting it be available for other processes to take. So yeah, like free. It's a better way to call it. It's a better thing to say. What we have to do in that freeing function is, well, first what we did in here, just flood with null, right? So just set the entire segment to null. And the other thing we have to do is save the offset to the aligned size, right? So we need to push, right? We need to push into that, and the way we would, I describe it because I need to think about it, and when I describe it, I immediately know. I sort of start thinking like ways to do it. So yeah, let's just say free name, and I guess what we would like to do is, well, like I said, well, first we need to fetch the pointer itself, and that's just self elements name, right? And from there we can say pointer flood, right? And we put null, right? Just to know that that thing is now available. I guess I could put free block in there, but yeah, like whatever. Like just letting you know, do not dereference this, right? Just telling you, do not dereference this. You shouldn't. Now that I think about it, I guess marking it as null would be telling you this is going to be deallocated, right? So maybe free block is a better, yeah. Let's say free block. All right. Yeah, because like null is what I would put when I'm going to free, right? When I'm going to deallocate, right? So like that memory is not going to be available anymore, right? So that's when I would use null. Okay. All right. So let's fill that with free block, and we need to save the offset. So pointer already knows its offset. And its type, so we can calculate this same thing. We just take this from the pointer. All right, do it like this. Instance count. All right, so it's basically the same data, just saved to the pointer. Having the aligned size, we can look into our hash, and so what I'm going to say it's on the block itself, let's say seg, because I don't have a better name for this. Let's say seg or segs. Would you like segs? Nah, seg. Okay, so I'm gonna say seg. So self seg at aligned size, we're going to default this to an empty array, and if this thing is already defined, then it will not overwrite it, right? So this is basically checking existence of the key before assigning, right? And if the existence check fails, it assigns an empty array. Okay. So now that we have our array, we can just push, right? And what we want to push is the offset, and so we need to get the offset, and the offset is within the pointer. All right, so the pointer already knows. Okay, so basically we are saying if you need another block of this exact size, I got one for you, right? So what we do in here is we check for that. Okay, so it would be self seg. Actually, let me shorten that just because. And let's add some documentation. Check existence of equal of free block of equal size. Right, that's clear enough. Actually, I think segment is, yeah. Say segment of equal size, and oh, let's say chunk. Why not? Nah, let's say seg. Let's say nah, let's say seg. Yeah, names are always a pain in the ass, but anyhow. So let's say what would be the opposite? Just row the block if non-available. Right. Right. So this is clear. I think this is clear enough. Right. So it's and it's pretty clean, right? Because both are just like one line. You don't really have to think too much about it, right? And actually, this is seg. All right. Okay. So basis, this is like, you know, good enough for starters, I think. Let's actually try it, okay? What I'm gonna do is I'm gonna say I'm going to allocate. Like first, let's just allocate and make sure that that still works, right? And yeah, let's just see what happens. And it's going up. Okay. All right. So we have a whole bunch of errors. So I probably forgot offset. I probably forgot declaring offset, didn't I? Yep. Yep. Again. So let's just say my offset. Right. All right. What else? To 70. All right, so I must have messed up somewhere. Let me see. Just zoom out so I can read this better. 90. Oh, My bad. Just doing some fast debugging of this. Okay, what else? I forgot to declare it. Yeah, forgot the my. There we go. Okay, so that works. All right, let me clear the screen. Let's test this again. Okay, and there we go. All right, so allocation still works. Now let's try freeing. And oh, I actually have to pass the name. Yeah. Oops. Yeah, like probably I should do it pointer free, right? Like that would be a better way to do it, but just to test this. Oh, right. You see, it's like the natural way to think about it. So we have to handle that somehow, but yeah, we do handle to create this. Okay. So now let's try allocating again, right? And if the modification we did onto alloc doesn't work, we'll find out because it will grow the block, right? And if it doesn't grow the block, then we know it's right. So let's try, and it frees it out. Oh yeah. Okay, that's nice. If we do not free, it gives us another block, right? But if we do free, we say we can reuse this. Okay. Now let's try asking for a type of another size, right? So let's just say that type is now equal to, I don't know, let's say 5 wides. Oops. Let's say 8 wides, something like that. So that should be 16 and 32, I believe. Yeah, it should be 32. And yeah, I'm just giving it the same name. It doesn't really matter. And yeah, it frees the first one, but it cannot reuse it because it needs a block, a segment of a different size. You see? So yeah, pretty fucking cool, no? So okay. Well, I think let me just check something real quick. Okay, so it took me about an hour. I thought it would take me a little bit longer, but yeah, no. You know, and you know, like quote unquote an hour, because like half the time I'm just talking and drinking and smoking and whatever. Because yeah. So anyhow, so okay. Next up, we would have to look into actual the allocation, right? So shrinking the block. So instead of assigning free block to all of this, what we would do is just shrink it. But the problem is, you can all, because of the model that we are using with, like I told you, with break or S-break or whichever one of the two, rather than mmap. Like I do have mmap, but I just for a challenge, I want to do it with break, and just because it's easier to think about. And plus, you know, like having the whole thing be contiguous, it's kind of neat. So yeah, I'm just doing it like that, and you know, I'll add like a mmap kind of alloc later on. But for now, this is pretty much what I want. We will have to handle shrinking the block, right? But the problem is we can only shrink when all of the, you know, if all of these would have to be thread, right? All of this would have to be thread, and if that is so, then we can shrink. But if all of the blocks from the top to the section that we want to free are not have not been thread, then we cannot shrink, right? Because we still have data. Well, you know, we can shrink. As a matter of fact, let me just demonstrate that. Okay. So basically, it's just the inverse operation, you know. We don't even have to do that. We just have to cut this, right? So basically, we have to say Let me think about it for just a split second. I don't need this thing. I do need the aligned size, right? Huh. Just gather my thoughts here for a second. So we can shrink the block. What do we need to do? We will do it with a substring, right? And that's basically this. Like, yeah, there's probably a better way to do it, but I'm just gonna do it like this, just for demonstration. And we need to lessen the size. And I guess we should return new top, maybe. Right, let's say. I just for clarity. Nah, I can do the clarity with a comment. Yeah. Okay. So, how would we handle this? Well, we would have to go from end minus size. No, wait, I'm sorry. From begin to end minus size, right? So end would simply be this thing right here. Top. And now we need to solve what size is. Well, if we only grow in aligned quantities, then we only shrink in aligned quantities. And now this comment is outdated. Because it's just easier. Just simpler to do it like that. Okay. So we take multiplier, and so what we have to do is basically say that size, that would be alignment times mult, right? And yeah, the multiplication should be first and then this, but just because it fucks with my brain not doing it like this, it does fucks with my brain. So anyhow. All right, that's neat. That's neat. What the hell? Let's just try it and see what happens. So let's shrink it. Shrink by 2. All right, so that works. If we shrink by 1, okay. So the problem with this is that we would have to make sure that all of the pointers within the section that we are shrinking have been fred, right? So those pointers no longer exist. That's the thing we will have to make sure of. And by the way, regarding 3, we would have to delete this pointer. Yeah. Because it has been fred, it no longer exists. We want to get rid of that. So let me just check if that calls the destroy. I'm just going to make a destructor real quick, just to see that it is being called. Okay, I think it's like this, destroy, but I don't remember what the arguments are, so let's just check. gonna say args, and so map say arg for args, right? And let's just do that and say bye pointer. Okay, all right. What happens? Bye pointer. All right, and so all right. So it gives me just the instance. That's nice. All right. Okay, so destroy is being called. So yeah, the instance is being eradicated. I can just leave it like that. Or actually, I don't even need to implement it because I know that when I deallocate when I free it, I'm sorry, I keep using terms interchangeably. I'm sorry, but yeah, it's just weird inversions going on within my brain. But anyhow, whenever I free the pointer, I know that the destructor is being called, and so no problem. So, like I was saying, we would need to make sure, you know, for actual deallocation, we would need to make sure that before we shrink the block, we will need to make sure that all of the pointers from top to end minus top, right, to top minus size, I'm sorry, right, so the segment we're trying to shrink, we would need to make sure that all of those pointers have been fed, right, because if not, then we would be losing information that might be in use, which is not what we want. And we would, you know, wind up with a bunch of just, you know, dangling pointers, you know, still living within the elms hash, right? So we would still have the pointers themselves within the elms, right? We would still have them, but those pointers would still be there, but they would be pointing to memory that might no longer exist, right? So that's no good. That's no good and not what we want. And so yeah, we would have to take care of that. But yeah, that's, I guess, what we're going to do in the next episode. And well, that's it then. I'll see you then. You know, bye. Have a good one.